Okey-dokey. Well, we'll start then. Hello and welcome everybody, and thank you for joining us for today's Durham Energy Institute seminar. Today we've got Dr. Gagangeet Aujila, who's one of our fellows at Durham Energy Institute. He's an assistant professor in the Computer Sciences Department at Durham, and he's had academic positions in Durham and in Newcastle, also in India and Austria previously, and he's won various awards, including an IEEE Early Career Researcher Excellence Award, which is brilliant. And Gagangeet's going to talk to us today about energy trading in SDN-enabled smart transportation systems. So during the seminar, if everyone wouldn't mind turning off their cameras and muting themselves, we'll listen to the talk, and then at the end we can turn back on cameras and have a question and answer session. If you would like to put your questions as you go through into the chat on the Zoom function, we'll keep an eye on those, and then we'll come to questions at the end. So I hope that's all right, and over to you, Gagangeet. Thank you.
Yeah, thank you. Thanks very much for a nice introduction, right? So welcome everybody for this talk, right? I'm Gagan, right? So today's talk will be focused on one of my aspect of research. Although I'm a computer science person, so we focus, the work I do is basically on software-defined networking, distributed systems, and blockchain and kind of thing. But energy is also one of the part of my research domain. Actually, I did some works starting from a PhD and postdoc until now. We are still working on this kind of stuff, which is related to sustainable computing and energy trading and electric vehicles. So this is one of the work that me and one of my colleagues at same in computer science we did. We started working on this in 2018 actually, and it's still ongoing with the various incremental stuff. So just to make sure, can you see my screen?
Yeah.
Yeah, because on my side it's showing your screen sharing is paused. I don't know.
We can just see your first slide at the moment.
Yeah, I can. So is it moving right? No.
No.
Yeah, actually. So I'll reshare it now, maybe.
Okay.
So is it visible now? Right?
Yeah, that's moving now. Thank you.
Thank you. So the title of this talk is Energy Trading in SDN-enabled Smart Transportation System. So I'll briefly go through what I will cover in this talk, is starting with a brief background about some aspects of electric vehicle. I'm not energy or electric vehicle guy, so I'm a computer scientist. So I'm not sure how much I try to meet whatever best I can do in this energy sector, right? So next we'll move to the challenges in the domain we have considered and what the leverages we have, some troublemakers, and what is the need of this work. And then there's a proposed solution which moves across with multiple variants, where we have energy trading dual strategy, we have mobility model, we have pricing model, we have SDN strategy, we have some secure strategy and energy coins, and EVaaS and efficient scheduler, right? Finally, some validation and some preliminary results we have. So I'll start with the background. Most of the things, anybody who is from energy background knows this. So transportation and energy sectors have, witnessed a huge revolution in the past many years. And one of the end product of this revolution is electric vehicles. So traditionally, transportation sector has been dependent on the fossil fuels. And, they attribute to like 1/4 of the energy related to carbon emissions is attributed to transportation sectors, which actually is aimed to reach 1/3 if at the pace it is going. So the thing is that we, in order to stop this kind of growth, we need to do something, and most of the countries across the world are trying to put their bits and pies to resolve this issue. So in order to reduce the air pollution, one of the major challenge we have to do is to make low and middle income countries a part of this global shift. Which most of the developing countries are already doing. Like in Great Britain, there are some targets that we are following, that 80% of new cars and 70% of new vans sold in Great Britain to be zero emission vehicles by 2030, and it need tend to be increasing to 100% by 2035. So even if we are not able to achieve 100% targets, but still whatever steps we take will be helpful in achieving a larger goal. So just talking about some benefits, quick benefits, right, of electric vehicles. Where there are multiple benefits attributed with EVs, right? One of them is that they are environment friendly. They do not produce any direct tailpipe emissions that link to CO2, nitrogen oxide, and greenhouse gases and harmful pollutants. Additionally, their life cycle emissions are also minimal as compared to a fuel-based vehicle. And these life cycle emissions, again, include harmful pollutants and gases that are emitted in the process of production, processing, distribution, use, and reuse phases within the vehicle. And so they are capable of bringing down the overall pollution level attributed towards the transportation sector and help to improve public health and reduce the degradation of ecological environment. Also, they can help us to save some bits on fuel consumption. Right. So some statistics: an average EV owner can save about $30,000 on fuel costs in a lifetime, with annual saving about, this is some reports that claims this. So additionally, they say that the maintenance cost is very less as compared to fuel-based vehicles, and they are quieter. EVs are quieter as compared to fuel-based mechanisms, right? And if you look into this figure, it depicts different stages where energy is consumed throughout electric vehicles and gas vehicles, and it's clearly depicted that EVs can also help to recover and regenerate energy, and the efficiency on tentative efficiency or average efficiency they achieve is 87 to 91%, in contrast to other vehicles, which the energy efficiency is 16 to 25%. So looking into these benefits and these positive sides of electric vehicles, there have been huge growth in EV deployment across different countries. One of the positive side of this is that numerous government efforts, subsidies, and initiatives also pushed up this in terms of zero car tax, capital allowance for companies, kind of things that pushed that growth of EVs across on the roads, right? Global EV Outlook predicted 500 million EVs on road by 2030. There are different reports that can have different figures around it, but ideally, it's expected that EV sale will reach around 40 to 50 million per vehicles per year by 2030, right? So this is just one statistics within UK in 2015, EVs on UK roads were just 1.1% of overall vehicles, but in 2020 they became 10%, and currently they are much more than, and within 5 years it will be too much, right? So with this growth, there comes the problems. So one of the biggest problem that this growth brings is that EVs form a very large energy network. So we try to visualize some of the facts. This is a Durham city center, and also a random location in UK. So it shows the deployment EVs and charging stations across different locations. So forming this larger EV network, if this network is of a normal vehicle, it have different problems. But because this is electric vehicle, and it depends strongly on, these vehicles need energy to, make their things work. So this kind of network has their own challenges. So one of the biggest challenge of this network concern is that if this large network is not handled properly, then it may put an additional burden on the overall energy utilization of a power grid or any country overall energy utilization profile. However, if it is handled optimally or properly, it can be leveraged to develop sustainable cities. Another key concerns are related to charging times. Currently, it takes anything about 30 minutes to 24 hours, depending on the size of battery, type of car, charging point, location of the charging point. There are many dynamic aspects around it. And also there are some issues related to charging points. UK still facing charging point shortage, leading to longer travel distances and potential queues. Government has started with various initiatives via grants through local authorities, but still a parliamentary report criticizes government for inadequate development of network charging network. This national charging network. So this is just a statistic about UK, but if you think about different countries across the world, the situation is much more worse. So we know that there are some benefits of EVs, there are some concerns, but do we have any leverage, right? So we have leverage that EVs batteries can be used to store, transport, inject energy to and from the grid as and when required. So they can be leveraged as energy carriers, and they can be used to manage the grid load or load of local areas to maintain energy stability. And this can be, achieved by, moving the excess power of EVs across the geolocated charging stations. Right. And on the other hand, whenever the charging stations require some energy, they can absorb energy from EVs whenever required. So this kind of scenario, if we want to realize this needs different aspects to be achieved. One of this is an efficient energy trading mechanism that can understand the overall demand profile of local charging stations and also the requirements EV, and put all together and formulate them to a solution that can be a win-win solution for both parties, for both EV owners and charging stations owners, right? So another benefit is like one of article in Yi et al. Published in ICC. They said that the traditional way of transmitting energy through grid has average loss of 25% in contrast to the losses of 10% that if we transmit it through EVs, right? So this motivates us to use EVs as green energy carriers across the cities. So, but still there are further some problems when we talk about this kind of solution where we use EV as an energy carrier. Some of the major challenges associated to realize this is related to EV's mobility, like users' destination, state of charge of battery, location of EV, location of charging station. And so this need to be modeled accurately for understanding EV mobility and embedding that mobility aspect into overall energy trading solution. And it's not possible for EV to travel instantly from one location to another because it has to it comes across different challenges like traffic on road, distance between the EV and destination, and different bottlenecks that come across in communication and all. So it's very important to consider all these factors while designing any demand response or energy exchange solution. So there are other concerns also related to like pricing mechanisms. There are most of the time we have fixed pricing mechanism or we have time of use pricing mechanism. They don't consider a number of aspects like vehicles location, vehicles type, and energy demand at a specific time, and charging stations location. So these kind of factors also need to be considered while designing any possible solution for energy trading and such. So what we need is basically we need to design and develop an effective energy trading and efficient scheduling mechanism that considered multiple aspects like keeping price of charging low, keep minimum time where one has to spend driving to a charging station. It also need to consider minimum amount of time spent charging. It also need to consider where charging station is located, reduce the queuing time. It also need to consider if enough battery is left to get to the charging station, and also how much time it will add to the overall journey of a EV commuter, right? And finally, some aspects like differences in vehicles, chargers, and batteries. And finally, one of the best major thing these days is popular is user preferences, what user wants, right? The solution needs that also to be considered. So keeping in mind all of the solutions, all of these needs and troublemakers and concerns and all leverages, we propose a solution, a novel concept, which we called as electric vehicle as a service, which helps us to realize an energy trading mechanism between CS and EVs in a typical smart city scenario. So early findings were published in 2018 in Computer Networks. This architecture considered different factors like mobility, battery, energy required, dynamic changing patterns of charging station, which are considered while making energy trading decisions. And this model works in two layers, dual strategy, where EV can act as a buyer and EV can also act as a seller, right? So it's a leader-follower game that we follow in this mechanism. And this solution has multiple aspects, multiple submodels, subtasks. One of this is how we model the mobility of the vehicle. We use two mechanisms. First is a grid-based method that is for any ideal planned smart city. Alternatively, for an unplanned city, we use the sumo-based electric vehicle ad hoc networks method to understand the mobility or movement of vehicles across the city. And then we consider we design a pricing model. Basically, we use two methods. One is time of use along with our proposed pricing model. And second is we propose a multi-parameter pricing schema I'll talk about a bit later. And third is we design an intelligent scheduler that generates EV charging profiles and provide optimal charging station recommendations. It's the current ongoing work just finished. So next is we have a SDN-based communication framework. I'll not talk much about this because I don't want to drift towards my core communication domain. And finally is a secure, because there's a lot of data movement across this entire scenario in large networks. So we need to make sure everybody participating in this mechanism is authenticated and their authorization levels are maintained and data integrity is maintained. And to push EV and charging station owners to join this kind of mechanism, we have an incentive energy coin mechanism based on blockchain. So just overview of a typical electric vehicle as a EVaaS model. We considered three different areas. One is residential, commercial, and industrial, where charging stations are deployed. So for simplicity in this figure, there's only one charging station deployed, but depending on the size of area, how we typically describe the grid-based method. In each of the grid, we have one charging station located. So these charging stations are linked to the local energy demand. So they have different dynamic patterns because different areas have different load profiles, load demands, and trends. So that's why we consider three different areas. And there are EVs that move across the smart city in these areas. So it also depends for different areas, the mobility of EV at some locations or some time movements are different in different areas. So all of this is connected to a gateway that connects them to two basic components. One is a service controller and second is a SDN controller. I'll talk one by one about all these aspects. So these charging stations, which are located in these three different load profile areas, depending upon their power requirements, they try to trade with electric vehicles to maintain their battery pools, right? So whenever they have deficit of energy, they can request energy from EVs, and whenever they excess energy, they can sell energy to EVs, and EVs can take that energy and provide that energy wherever there is a deficit. So the load requirement of charging stations is gathered as a central server, which we call as a service controller or service aggregator. And this server broadcasts the request to EVs, which then calculate the net profit based on the energy trading mechanism. And then they decide based on the profit function which charging station they want to go. So this is basically the service controller, which takes requests from different, basically this communicating bridge or hub between EVs and electric vehicles. Because it's a multi-leader, multi-follower mechanism, there are multiple EVs, multiple charging stations. So all the requests are collated at this aggregator service controller. And then it, based on the conceptualization of the profit functions that we considered in this work, they decide which EV will go to which charging station, or alternately, which charging station will supply, take energy from EVs. Right. So this is another aspect. So there are a large number of EVs and charging stations communicating with each other. A lot of data is moving across this entire ecosystem. So we decided to use a more flexible and reconfigurable network paradigm that's why we use a software-defined networking mechanism because it allows us with more scale, more agility, more flexibility to do things as per our requirements. We also wanted to prioritize the different requests from different kind of electric vehicles. So SDN provides us a way where we can prioritize the data packets, and our flow table mechanism, which we designed in this work, allows us to handle that traffic differently. So that's why if you see across this figure, we have different kind of there is an end host source to destination, which grows through different hops. And we have a physical flow table that is deployed over each of the forwarding device in a switch or router. And over that physical flow table basically tells the incoming packet where it has to go to the next hop. Those flow tables, using the SDN architecture, we create multiple virtual flow tables, which are segregated or reduced from an overall flow table to be divided into multiple flow tables based on different prioritized flow rules and flow entries. And if we don't have any matching flow entry, then we have to request to the SDN controller, which on the run can decide a new flow rule and install on the flow tables. And then the packets follow that flow table rule to move across how the packet will be treated in this entire network. So because as I highlighted, EV mobility is important. So the first thing we consider here in EV mobility is a grid-based mechanism. We ideally assume that we have a typical smart city scenario where we divide the city into different blocks, D by D blocks, in order to model the EV mobility. Each block may consist of several EVs and charging stations. However, for simplicity, we only considered one charging station in each block, right? So, each EV would prefer to trade with the charging station present in the same block because distance is near, but this may depend on different other methods also. Like in the pricing method, we have different other aspects also that may differ. EV may differ its preference of location or distance. Instead, it can go for another aspect. So the distance and profit of EV sometimes may be same. So in that case, EV as I can choose based on the user preference. So let's take an example of this grid-based mechanism. Let's take that there's an EV located in the center of this scenario, and there are 4 charging stations located at A, B, C, D locations. So what ideally we do is that we try to compute the distance between EV and charging stations. That is denoted by this D XY, where X is the position of EV and Y is the position of charging station. And the distance between X to Y is the actual path they has to travel from actually on the map, right? So this is the formula equation number 1 that we use to compute the distance between X and Y, where dx in this is distance of X from the end of a block, and dy is the distance from end of a block of charging station, and d is the fixed distance of one block. So these are equally sized blocks, so it's easy to compute. So nx to y are the number of blocks that are present on the way from when we travel from X to Y. So if in the example I talked about, if we want to compute, so we see a charging station has an EV in the middle has 4 charging station options, and then it computes the distance ideally based on these equations, and then compare the distance preferences. So this is just one of the results. I'll talk about later in the end how these options and preferences are provided to multiple EVs based on distance. Like if you see in the the first part of this over here, we have a red bar on the top, so that's the maximum distance that EV needs to cover. And alternatively, there are 2 distances that are lower. So this distance is from for EV to travel to a charging station is one of the key parameter that we consider in energy trading decisions, but it's not the only parameter. So the second part of this mobility model was when we considered a sumo-based simulation of urban mobility is a popular tool in vehicular ad hoc networks that we do. So we created a EVaaS electric vehicle ad hoc networks, and we used this sumo tool to actually realize the real-time movement of vehicles across a city when there is no planned grid-based location available. So this leverages all the vehicular to everything communication paradigms and helps us to mitigate communication costs and delays in delivering the charging request to the global aggregator, that is, you have a service controller. So as I said, its distance is not only a aspect. The second major aspect we consider is the pricing model. So pricing model is one of the key to this energy trading decision. So the energy price is set by a charging station when it has to sell energy, and by EV when it has to sell their extra energy. So based on these price, the EV owners, charging station owners, can decide how to trade. So I can just. So first of all, I'll talk about the price that at which an ith EV would sell its energy. So PSI is used to depict the price at ith EV will sell the available energy with it. So we consider this based on a maximum state of charge of ith EV's battery and its available state of charge, and we consider a threshold value that's dynamic, right? We can change it as it can be as per the owner request or can be based on the historic data. Right, so they intend to maintain this threshold value, and there is a constraint that the selling price should always be greater than the buying price that the EV owner charge, right? And this threshold is decided, in advance. And we have a scaling constant which we use that to make sure the selling price is always greater than buying price. So next, just a second. Right. So next, sorry. Yeah. So next we decide, now charging station also has to decide a price. So they decide the initial price that which they will sell, again based on the maximum state of charge available and threshold. And we also consider scaling constant to make this value above 1, because at some values we find that this value got out of bounds, so we have to scale it down, use a scaling constant. In the pricing model for the previous two aspect, which we consider is more dynamic, right? It doesn't consider any, basically in the starting, it's a fixed price. Then we move on to consider a time of use pricing. But later on, we thought of considering further more features or parameters into this overall mechanism. And then we decided to design a multi-parameter pricing mechanism. So basically this MPPS, which we designed and published in JPDC in 2019, which consider, I have mentioned 3, but there are 4 factors. One is time of use, second is location of charging station, third is type of EV. So time of use is based on the available energy, or energy demand at a specific location or area or where charging station is located. It doesn't only consider charging station demand, but it also considers the energy demand profile of that local area also, right? And based on that, we decide there is a peak time and off-peak time. But there are some times which we feel that the threshold between the peak and off-peak time, the ranges close to that threshold will look like it's biased, like they can be into any of these ranges. So we further decided to segregate these peak time and off-peak time into subparts. So then we decided to make it's like low off-peak time, high off-peak time, and low peak time and high peak time. So we have 4 basically time of use ranges that we consider to make it more dynamic, right? And then we also consider area in which charging station is located, right? So there are sometimes some areas are very demanding areas, very busy areas. There is huge demand of a queue of EVs that are looking for charging stations. So that adds to their delay and long queuing times and long charging times. And the availability of those locations are not always available. So we try to give a leverage to some of the areas where the locations where the charging station are located, and they are not so densely demanded by EV owners. So we try to, like, sometimes it's there is a EV charging station on the highway and it's too popular, and there is a charging station just a bit lower than highway, then it may not be very popular among the EV users. So we try to give them a incentive part that we consider pricing scheme. That pricing scheme will vary for these different areas and location based on their how congested they are, right? So the aim was to reduce the overall waiting times of EVs and reduce the queues on the charging stations. And then another aspect we consider is type of vehicles. So we try to prioritize some of the vehicles, some emergency vehicles, or some vehicles like, there is a problem, like we can take an example of some congestion areas across UK, where local, people who stay there, they have to sometimes face inconvenience. So we try to add this aspect in the pricing incentive model, where we consider that they may get some incentive out of if they are charging outside that area or within that area. This is if a vehicle is outside that area and is charging in that area, they have to be compensate, and that proportion will be given to people who are facing inconvenience. So this is the first part of energy trading mechanism, is when EV acts as a buyer. When EV acts as a buyer, it acts as a leader. So it initiates the charging energy trading requests. It requests for energy that it requires. It sends the vehicle ID. Vehicle ID will decide the type of vehicle, type of battery it has, and type of area which it is registered to, is local or external or so, because the pricing mechanism have to take all this into account. And the aggregator send this request to charging station. That is a follower. This is a leader-follower Stackelberg game, actually multi-leader, multi-follower, where the leader has a leverage to put up their requirement at first place, and then the follower has to reply with a price. And there is a problem here: the follower cannot backtrack from the price they have once committed, right? So, but the leader can again update their energy requirement based on whatever the price they get. So finally, if they decide to agree on, based on what we'll talk in a couple of slides on their utility function and profit function, if they try to agree based on Nash equilibrium stage they reach, then EV will travel to the charging station to charge their batteries. So now how things work I'll not go too much into these equations, right? So the first thing is that the first thing decided is that every EV who is participating in this energy trading request have to compute their required energy, that is based on whatever status of their battery is at current time and the maximum energy and rated capacity, and then they communicate that required energy to an aggregator, and then aggregator pass to charging stations. Similarly, charging station also has to compute their available energy, that is given by this E available, right? So this E available will decide basically what kind of what energy is available with the charging station at that time. So that's again based on the threshold value and present status of their battery pool that they are connected to, right? And the aim is always to consider that the present status of their state of charge of the battery pool is more than a predefined threshold that they consider. So then another part is So after the energy trading deal is agreed, EV has to travel to the charging station to get the required energy. And after they have to update the status of their battery pool and then communicate back to the aggregator, because the next round of energy trading, they may be participating in another different scenario. Similarly, so to compute the updated request, they also have to consider the travel time and the energy they consume while traveling from their current location to the charging station. So that's where they discharge some of the battery, and then they consider that aspect, and finally they can compute their updated energy status for the next round. Similarly, when charging stations supply the energy, they also have to do same. They have to update their energy status and broadcast it to the aggregator for the next round, right? It depends on their present state of charge and also the energy they have given to in the previous trading round to an EV, right? So this entire thing depends upon the utility functions or profit functions. One of them is in equation 16 in front of a utility of electric vehicle. And it is based on three aspects, basically: the energy required multiplied by the price that is quoted by charging station, reducing the travel time, and the price at which they have to compensate whatever energy they had dissipates while traveling. So the goal of EV is to maximize their utility function, keeping some constraints that their required energy should be greater than zero and less than rated capacity, and the price at which this P price with respect to energy what they spend should be less than or equal to the revenue they have, right? And same way, charging station also has a utility function. They compute this utility function with respect to other set of charging station available at the time. They try to provide a strategy or a price that is best in contrast to all the available charging station at that time who are participating in energy trading requests. So their utility depends upon the price they quote and energy they are replenishing for the EVs. And there are some constraints, normal constraints that they consider. And both of these parties trade with each other with the aim to maximize their utility function. So I'll not go much deeper into how this actual equilibrium state is achieved. So based on the inequality variations and other, they achieve an equilibrium stage where they achieve on a win-win situation. Both parties cannot deviate from that strategy, and they agree on that optimal decision. So second dual strategy part is when EV acts as seller. So I'll just ignore this part because we have time limitations. So this is just a reverse where EV is a selling party. They have to compute their available energy, and charging station is the buyer. So they have to request for whatever energy they require from EVs. So in this mechanism, there is difference, but because there may be different EVs that can collate together to replace the demand of charging station, because they may have limited energy available and charging station required will be more than that. So one of the another aspect here is that initially, I think I missed it, that all the charging station are connected to two energy sources, three. One is the battery pool, one is they are connected to some renewable energy sources like PV panels, and third is they are connected to grid. So first, they try to fulfill the required from the solar panels. So when we try to compute the energy required by EVs, then we have to consider that how much energy they can extract from the renewable source of energy. And the last option is the grid. Second option is the EVs. So they decide their required energy based on all these mechanisms, right? So again, similar kind of utility functions, they agree on these decisions. So that's how the energy trading happens based on the utility functions. And finally, I'm moving on to the last aspect of this talk is efficient charging scheduler. So we also developed this charging scheduler that is more intelligent, and it considers a real-world simulation of the actual environment on Sumo and NS3. And on the other hand, we have a deep learning solution that try to create energy profiles of all the EVs and then consider those based on whatever their requirement is. So there are two layers of this work. One is where we have Sumo traffic simulator, where we actually emulate these vehicles moving across. And from there, we generate data and we train our deep max out networks, which try to predict actual power requirement of those electric vehicles on the go in the real time, and then feed to our electric vehicle ad hoc network. And then they send those predictions to the global scheduler. And on the other hand, we have a virtual autoencoder and XGBoost machines, which we train based on a defined data, right? So we faced a problem here because we didn't have a very accurate or quality or very, a data that can cover all the aspects we consider in this. So we trained this machines all based on whatever possible data we have, and then we train this VEA and XGBoost and optimize them. And both of these outputs go to global scheduler, and then they try to compare what we get from the actual scenario and what we get from the predicted scenario. So I'll discuss this more in the results. So to validate this mechanism, we considered multiple case studies. The first case study is where we consider the pricing scheme plus our energy trading only, right? So here we considered 4 charging stations located in different locations, and data used to considers from Hawaii Island State Energy Office. And we have different parameter settings that consider. We use time of use pricing offered at Hawaii Islands, and also later we move to our multi-parameter pricing scheme, right? So and finally we updated it to more realistic Durham city scenario, right? These are some specifications of the chargers, level of charges, number of chargers available at different locations, what access times, and our battery specification of different electric vehicles, and state of charge and thresholds which we consider. So we have some results. Initially, we compute whatever is available state of charge or energy present with all the electric vehicles, and we consider the threshold. Whatever is above the threshold can be utilized to consider in the energy trading mechanism, right? Then we compute based on whatever current status or present status of the batteries of EVs are, to compute what energy they require. Some of the EVs may require energy, some of may have excess energy, so they can trade accordingly, right? So similarly, we also compute the energy available at that time. So this fourth figure shows the all collated scenario where some of the EVs may discharge, some may have charging requirements. So then we move on to our pricing mechanism and our distance. So first aspect this mechanism computes is on optimal price that is offered based on energy trading mechanism. And then second is what is the distance. And then finally, we consider both of these aspects, along with the travel time. So this part A considers a travel time that all the EVs have to travel to move to different charging station options. And based on all the three aspects, we compute this utility function, right? So the goal is for charging stations, for EVs, is that they will go to the charging station where their utility function is maximized. And similarly, but that's always not preferable. But when you put a user preference into it, then they can consider based on their own choice where they want to get. So once optimal charging station is selected, they move across and charge, and then their state of charge is updated. And so these two provides an updated state of charge with respect to a charging station selected and with respect to all the charging stations. So the mechanism provides you all the options, and then you can utilize that to finally decide on which charging station you want to go. So another part is for charging stations. These are some visuals for charging stations, some plots where we say at that current in the simulated scenario, what was status of those charging station at time when they want energy and when they have excess energy to sell, or when they have deficit and when they want to charge. So this is the perspective of charging station with respect to different EVs in this scenario. So we have considered these 10 EVs, and all the charging station will get all the price, distance, utility based on all the 10 EVs, similarly to what the EVs got from 4 charging stations. So, and finally, they decide their utility function, and based on that, finally, we have a selected EVs where they travel, decide in this D part, EVs-as-a-service. So then in second case study, we consider a Durham city center scenario using Sumo in front of you. Is like, and here we use a multi-parameter pricing scheme where we use time of use, location of CS, and type of EVs, and then we compare it with the baseline fixed pricing system and its only time of use price mechanism system, and see how our mechanism provides a benefit. So so the first ones are just energy demand of EVs and distance and the price. If you look into fourth figure here, that's price based on different mechanisms. So fixed price may be lower than the time of use pricing at some occasions, but multi-parameters pricing scheme offers a more competitive pricing and less than the time of use pricing mechanism. And here we also consider a factor that we call a satisfaction factor. We design the satisfaction factor based on all the parameters and considering utility functions. So an EV will go for charging to go to a charging station where this satisfaction factor is higher. So if you look into the first figure in the case one, where we consider multi-parameter pricing scheme, different satisfaction factors are in front of you. So the charging station which provides you the maximum satisfaction factor will be preferred by EVs or charging station when they charge. So these all figures depict some of the aspects like different satisfaction factors of EVs, CS, and based on different factors like fixed pricing, time of use, and Mbps. And this also we consider try to analyze how this low peak, high peak scenario for special vehicles, outside vehicles, different types of vehicles can offer more variety of pricing to the overall trading decisions. And then finally we consider how we can schedule this EVs based on more intelligent mechanism. And then we simulated a Durham city scenario again using Sumo, where we considered 17 charging stations as per UK government data set. And we considered 2 types of charging station with faster charger being more expensive than other. In this scenario, because of the data we used to train our VAE and XGBoost was not covering all aspects, so we neither consider speed or price of charging station was considered, right? So, so in the first part of for virtual encoder, we generated data from EV charging simulation. We have a link over here that is from Aalto University, Finland, the data they have provided. We tried to prepare 2 VAEs, one for prediction of charging station that the requesting EV should go to, and one model to predict when EV should finish charging at a predicted charging station. So one predicts a possible or tentative recommendation of to which EV, and second provides the end time that at which the EV will get free after charging. the required energy from there. So both are trained and on same inputs. And initially we consider the training loss. So initially there was a degradation, but then it slowly balanced itself. But as I said, due to data limitations, there were some issues with this training process. These are two outcomes which we received is based on these two mechanisms, VAE and XGBoost. Initially, we planned to do with VAE, but the outcomes which was very, very static. All the times they were trying to predict same charging stations in the line. They were not giving us more variety or options. They were just selecting one optimal charging station. But when we used XGBoost, it gives us more variety, more number of charging station ranges and options which we have. So further, some more charging end time predictions, how when an EV, which the results remained almost similar, right? So we have with VAE, actual and predicted departure time is tending to be only on one balancing point and it's not following the trend. So in XGBoost, actual and predicted departure time was almost on similar lines. Second part, we consider data from our actual simulated scenario, EVaaS, where we use to predict total energy consumed by EV during its journey, right? When EV is traveling, at how much energy it will consume, and what is the time which will trigger a charge request within this entire scenario, and then they will request for the system to provide an optimal charging station where they can charge for energy. So this data is generated within from event scenario, and there were some abrupt changes in the training loss over the time. Overall, they were balanced. And what we found is that the trend of actual versus predicted total energy consumed were in similar lines. They followed the same trend. Finally, both the decision makings, both side of the mechanisms are moved onto the global scheduler, which then compare it with, so the results obtained over here are also similar trends. When we consider this first one is with, VAE, it always relies across a similar line, ranges from 6 to 8 number of EV number 6 to 8. But if we consider more charging station predictive, XGBoost it's variable. It provides multiple options of charging station recommendations. And then we have this user preference-based efficient scheduler mechanism, the small case study of app where a user can input some predefined requirements like current battery state and desired percentage they want to charge, and then this mechanism will provide them with optimal charging station options. So it will provide with them all the options and the price and distance from where, and they will also provide you the closest option and most affordable option. All right. So if you want to read further on this, there are some papers we have published in the past, right? You can look into this. And I guess that's all from my side. Any question I'm happy to answer, right? Something is there in the chat. I can just look into.
Thank you. Thank you very much, Gagangeet, for that talk. Does anybody have any questions that they would like to ask? Either pop them in the chat or you can just put your hand up if that's easier. I had one to start if no one else is driving in straight away. So I just wondered if you have had any discussions as part of your research so far with anybody sort of on the social sciences side, because it sounds like there'd be loads of interesting questions about how this would work, how people would interact with it, that kind of thing.
Actually not, we have not. Like last year, I have one student with which I was working considering user preference or customer perspective, but that work was still, didn't went through, But still it's interesting thing because there are a lot of social aspects into it, different. Yeah. The initial plan was like, okay, if I am traveling on a motorway and I want to charge, there is a requirement and I have some preference, like, okay, I prefer something on the way where I have charging station also, and I can go stop there to eat something and stuff, thing like that. Then my user preference, my requirements should be considered by the system. But definitely there is scope for, considering fact, right? But we have a project like with engineering, we have a virtual power plant, AI for Net Zero grant recently, EPSRC, where we consider this. We have a COI from sociology, right?
Mhm.
So they are in that project. We are definitely considering these kind of things, right?
Fascinating. Thank you. I see Colin has a question, if you'd like to.
Catherine, this is Colin Woodward. Okay. Well, firstly, Gagangeet, thank you very much for an extremely thought-provoking presentation. There was too much information for my little brain to take all in at the time. However, I'll declare an interest. I don't know where you are. If you're in Durham, I'm about 2 miles from you, and I do have a relatively small battery. But I found myself thinking, as a potential electric vehicle, if you like, what's in this for me?
So
before you answer, I'm being a little bit devil's advocate. You see, as I understand it.
Sorry to interrupt. There was some breakage in connection, so I didn't hear the initial part of what you started with. Right? Can you repeat it? Yeah. Sorry.
Don't worry. It was just thanking you for your presentation. I have an electric vehicle.
Yeah.
As I understand it, the scheme would be that when my vehicle is fully charged, and the conditions are right, I drive to a charging station and plug it in there, and it discharges, shall we say, 80% of the battery capacity or something.
Yeah. And
then I drive home again.
Right.
Well, that's not very convenient. And furthermore, it means that my car back at my home doesn't have very much electricity in it. So before I do very much with it, I've got to go back to the charging station and recharge.
Yeah. So that's one thing, right? Because this overall mechanism doesn't consider, like, it's based on the EV owner. If they have to decide, like, for example, I'm in my office and the whole day I have a fully charged battery and I have to stay for the whole day. And like, ideally, this idea came from a very self-sustainable building or data center where, like, employees of that, people working there go there.
Okay.
They have a fully charged battery, right? And let's say there's some assumption like that from where they charge energy is they paid less amount as compared to what they are getting when they have to discharge, right? So some of the buildings or those data centers have urgent need of energy, and the grid, the price at which the grid is providing is much more than that. So in that way, there is inconvenience, but that's the way to earn some incentives, right? And in that ideal scenario, where we started this work was that in the end of the day, that data center or that building will provide back you the energy that you require to go back sufficient up to the threshold you need, right? It's not like you give them 80% of that and you are sustained with 20%, but it will be a trading decision that you need it by the time in the end of the day up to 50%. So whenever they have excess, they will give it back to you. So there are many variants there. So
yes.
So that's why we are adding these things incrementally. Like, we considered some energy coin concept where we incentivize users who want to participate in this mechanism, right? The goal was to not invest more on infrastructure, but to schedule the things optimally so that we can use the same infrastructure. We keep on investing, and this is not a simple gas station. We need bigger locations, more machines, right? More charging points, right, where we charge. So it needs more investment in an infrastructure. In a typical fuel-based vehicle, we go to a gas station, we fill the fuel in a few seconds, a few minutes, right? So, and another car can come. But ideally, till the time we have a very efficient and fast charging scenario, we have to use the same infrastructure rather than investing more into that infrastructure. That's more. But user convenience somehow will be considered but we provide some incentives and other form of mechanism that compensate the user inconvenience, right?
Yes, I can see that it's almost individual convenience or not, isn't it? You see, as it happens, I work from home. I can totally understand that if you and 500 colleagues all drive your cars in typically at 8 o'clock in the morning, and you drive away at 5 o'clock in the afternoon. They can all be there either charging or discharging as appropriate. Yeah, at in effect, no inconvenience. Although, of course, at 5 o'clock on a Friday afternoon before a bank holiday, everybody wants their car to be full. Okay, thanks very much. I say again, very, very interesting. Thank you.
Thank you very much for nice words.
Probably got time for one more quick question if anyone's got one. No? Otherwise, there's a question about sharing the presentation. Just to say we've recorded.
I'll share. I'll email it to her. Yeah.
Wonderful. Thank you.
Thank you.
Thank you very much for that fantastic talk, and thank you everybody for joining us, and hope to see you at our next ER seminar. Thank you.
Thank you.
Bye.
Bye-bye.